Alright, so we'll continue where we left off in the previous video, and we'll try to do this hypothesis testing on the regression parameters, as well as a confidence interval for the regression parameters in Excel. So I'll start with our good old example of the pH levels and the yields here, and we did a linear regression using a method of least squares, and we got this model minus 1.68x plus 63.6, so that's our beta 1 and beta naught here. I'll just move it over here. What we want to do now is to do a full statistical analysis of these data here. So I'll go into data, choose data analysis, choose regression, and for my y values I'll choose the yield column here, and for the x values I'll choose the pH column. And notice I included the labels here, so I'll put a tick mark here. Excel offers to compute confidence intervals, and I can choose at what percentage. I'll just leave it like it is, but you could choose a different confidence level if you wanted to. The output level here is, or the output area, that's fine by me here. Right. And we'll click OK. I'll move this out here. And this is in Danish, so I'll do my best to translate. Our focus here now is to look at the intercept here and the slope. As you can see, you recognize these two numbers here from the graph here and the model equation. Right. And I'll just remove these residuals here because we don't need them here, like that. So what I'm going to do now is I'm going to do a t-test of the slope here. I'll just translate. Here we have the standard error and the t-statistic. Right. So the first thing we want to do is that we want to test the beta 1, whether that's significantly different from 0. And to do that, we need the test statistic, that's the one we have here, and we need to compute the standard error. Now, Excel has already done that, but I want to show you how it's done. So, the standard error for beta 1. And let's go back to looking here. What was the standard error for beta 1? Well, that was the square root of the mean square error number, which is our variance estimate, divided by the sum of squared deviation for the x value. So I'll write square root, SQRT in English, and we need the mean square error, that's this number here, divided by the sum of squared deviation. In Danish, that's sum af kvadrater på afvigelserne. I'm not sure what it's called in English. Let me just look into that. In English, I'll get back to that. I select my x values here. And close the bracket and close the square root bracket. So that gives me my standard error. You can see it's the same number here. In English, the sum squared deviation is called DEV SQ. So I guess that stands for deviation squared. DEV SQ. In Danish, that's SAK. So now we have the standard error. We can compute the test statistic. For beta 1. And if you go back, you see the test statistic is our actual beta 1 result minus the hypothesized, which is 0, divided by the standard error for beta 1. So that's the slope here, beta 1 minus 0 divided by the standard error. And you see that's the test statistic for the slope here. Then we want to find the p-value for beta 1. And that's no different than we usually do it. 2 times 1 minus, and then we need the t-distribution, t-dist, for the absolute value of the test statistic. And the degrees of freedom, I guess I forgot to say that. That's 20 minus 2, so it's the number of observations minus 2. And we want the cumulative distribution, so you write true in Danish cent, close the brackets. And here we see the p-value here. That's a very small p-value. That means that we can reject the null hypothesis. This one here, we can reject it and say that there's the slope of our model is significantly different from 0. So there is a linear relationship between x and y. That's what this test tells us. Right. Let's compute the confidence interval for beta 1. If we go back to the formula here, it says we take the actual parameter that we found and we subtract the relevant quantile, in this case the 0.975 quantile with n minus 2 degrees of freedom times the standard error. So I guess it's kind of standard procedure. So we take the slope, we subtract the t quantile, t inverse of the probability 0.975 and the degrees of freedom 20 minus 2, and we multiply that by the standard error for beta 1, and we get the lower bound of the 95% confidence interval here. So this was the lower bound, I should write that here, and the upper bound, just expand this column a little bit. Well, that's the exact same formula. See if I can copy this one here and change the minus to a plus. So what this tells us is that the true slope of this model here is somewhere between minus 1.13 and minus 2.22. And we can say that with confidence 95%. What that means is that if we took 100 samples from the population, or 1,000, a great number of samples, did this regression analysis, then 95% of the times when we computed this interval here, 95% of the times we computed this interval, it would actually contain the true slope. So we interpret that as this interval contains the true slope with 95% probability. Now we could go through the same computations for the intercept. It's exactly the same things. The only difference is that the standard error is computed in a slightly different way. We have the formula here. The standard error of beta naught is the mean square error times this number here. Yeah. A final thought here is to look at the ANOVA up here. The ANOVA does is about making an f-test comparing the mean variation in the regression and the residuals. So I think we talked in a previous video about the total variation in the y-value can be divided into a variation which is explained by the model and some variation which is not. And that's these sum squared deviations here. If we take the mean of those two and compare them by dividing them, let's write this here, we get an f statistic. So we take this number here, the explained variability divided by the unexplained variability, that gives us the f statistic. Now this f statistic obviously has an f distribution with two sets of degrees of freedom. The numerator of this statistic here, the numerator has 1 degree of freedom and the denominator has 18 degrees of freedom. So that enables us to compute a p-value. And really we should take the minimum of two different p-values, but in this case I'm just looking at the f statistic, noticing it's to the right of the number 1. It's greater than 1. So the way I compute the f statistic is 1 minus the f distribution evaluated at the f statistic with 1 degree of freedom, that's the numerator, and 18 degrees of freedom, that's the denominator, and true, or sandt in Danish, for the cumulative distribution. And there you see we get, it says significance f, but you could just write p-value here. It gives us a p-value, and that goes to show that there is a significant relationship between y and x. If you look at the p-value, it has the same value as the t p-value for the slope. And that's because we're really testing the same thing here. We're just doing it in two different ways. If the slope, I'm testing whether the slope is significantly different from 0. It's the same as testing whether there is a relationship between y and x here, a linear relationship. Because if we have a slope that's 0, let's just find another color for that. So imagine we have a slope which is, oh, that wasn't very good. Something like this. So that's supposed to be a horizontal line. If we have a slope that's 0, that means that the model gives us no way to predict the y value, even if we know the x value, because it comes with the same prediction every time, namely the mean of y. So that's the same as saying there's no, the value of x has no influence on the value of y. And that's really the same as saying that there is no relationship between the two variables. So that's why we get the same result here, even though we're doing two different tests. Right.